Mars calls to us across 140 million miles of darkness, a rusty beacon promising humanity a second home among the stars. We have dreamed of its canyons and ancient riverbeds, imagined cities rising beneath domed skies, pictured children born on Martian soil looking back at Earth as a distant blue star. SpaceX promises a million-person city within decades. NASA plans sustained human presence. China, the UAE, and private ventures race to plant flags in rust-colored dust. The machinery is already in motion. The rockets exist. The trajectories are calculated. We have solved radiation shielding. We have designed closed-loop life support. We can extract water from subsurface ice and manufacture oxygen from the atmosphere itself. Every engineering challenge, every technical obstacle standing between Earth and a Martian civilization has an answer, except one. One problem so fundamental, so woven into the very fabric of Mars itself, that no amount of money, no breakthrough in technology, no human ingenuity can overcome it. It is not a challenge to be solved. It is a law to be endured. And it may render Mars not just difficult to colonize, but biologically impossible for humans to truly inhabit. Tonight, we descend into the hidden darkness of the Martian dream. Not the darkness of its surface, but the shadow cast by a flaw we have chosen not to see. A silent killer that begins its work the moment boots touch Martian ground and never stops. This is not about dust storms or equipment failure. It is about what Mars does to the human body simply by being Mars. Something subtle, irreversible, and written into the planet's very nature. Before we journey deeper, I invite you to pause for a moment. Comment below and tell us where you are watching from and what time it is in your corner of the world. Are you watching at dawn in Tokyo, at midnight in Berlin, during an afternoon break in Sao Paulo? Let us know. We are scattered across this pale blue dot, but here, in this moment, we gather together to explore what lies beyond. Your presence here, wherever you are, whatever the hour, is part of this journey. So share your location and the time. Let's see how far this exploration reaches across the globe. Now, let us return to Mars and the question that haunts every colonization plan. What happens when gravity itself becomes the enemy? Not too much gravity, crushing us beneath impossible weight, but too little. Mars pulls at just 38% of Earth's strength. Stand on its surface and you would feel light, almost weightless, as if the planet itself is barely holding you. For a day, a week, even months, this seems like a gift, a feature, a liberation from the tyranny of Earth's pull. But the human body is not designed for liberation from gravity. It is sculpted by it, sustained by it, and when gravity weakens, the body does not adapt. It begins to fail, bone dissolves, muscle wastes, blood redistributes, the heart weakens. And the longer you stay, the worse it becomes, until one day you realize a terrible truth. You cannot leave, not because you lack a rocket, but because your body can no longer survive the return home. This is the fatal flaw of Mars, not its distance, not its cold, but its gravity, too weak to sustain us, too strong to escape unchanged. And it is a problem we can never, ever fix. We arrive at Mars with humanity's greatest ambitions carried in our spacecraft. The red planet hangs before us, smaller than Earth, yet vast enough to contain our dreams of becoming a multi-planetary species. From orbit, it appears almost welcoming. Rust-colored deserts stretch to the horizon. Ancient riverbeds carved into stone hint at water that flowed billions of years ago. Polar ice caps glisten white against the crimson landscape. This is the world we have chosen as humanity's second home, the destination of countless missions, the subject of innumerable novels and films, the planet that represents our future among the stars. But as our spacecraft begins its descent, instruments record something that no amount of enthusiasm can change. A measurement so fundamental, so inescapable, that it transforms everything we thought we knew about living on Mars. The gravity here registers at 3.71 meters per second squared. On Earth, that number is 9.81. Mars pulls at us with only 38% of Earth's gravitational force. This is not a minor detail. This is not a challenge to be overcome with better engineering. This is the fundamental design flaw that makes Mars not just difficult to colonize, but potentially impossible for humans to inhabit long-term. At first consideration, lower gravity might seem like an advantage, perhaps even enjoyable. Imagine lifting objects with ease, jumping 3 times higher than on Earth, moving with an effortless grace that makes every step feel lighter. For the first days, perhaps even weeks, the reduced gravity could feel liberating. Astronauts on the Moon describe the sensation of bounding across the lunar surface as exhilarating, a freedom from the constant pull that has defined every moment of human existence since our species emerged. But what feels like freedom in the short term becomes a prison of biology in the long term. The gravity crisis is unique among Martian challenges because it stands alone in its permanence. Nearly every other obstacle to Mars colonization has a theoretical solution: radiation exposure. We can build habitats underground or develop advanced shielding materials. The thin atmosphere? Ambitious terraforming proposals suggest releasing greenhouse gases from the polar caps, thickening the air over centuries. The freezing temperatures that average -80 degrees Fahrenheit, controlled habitats with heating systems, perhaps powered by nuclear reactors or massive solar arrays. The lack of liquid water on the surface. We know there is ice beneath the regolith waiting to be extracted and processed. The toxic perchlorates in the soil. Bioremediation techniques could theoretically cleanse the ground for agriculture. Each of these problems, severe as they are, represents an engineering challenge. Difficult, expensive, technologically demanding, but not impossible. We can build structures, we can generate power, we can create closed-loop life support systems, we can shield ourselves from cosmic rays and solar radiation. Humans have proven remarkably capable at constructing protective environments in hostile places. Antarctica, deep ocean research stations, the International Space Station itself. These achievements demonstrate that we can survive where nature did not design us to live, as long as we bring our technology with us. But gravity is different. Gravity is not a condition of the environment. It is the environment. It permeates every cubic meter of space on and above the Martian surface. It cannot be shielded against. It cannot be filtered out. It cannot be turned off or supplemented or enhanced through any known technology. The mass of Mars is approximately 6.39 times 10^23 kilograms. To change the planet's gravity, you would need to change its mass. To add enough mass to Mars to match Earth's gravitational pull would require increasing the planet's mass by a factor of nearly 3. There are not enough asteroids in the solar system to accomplish this. There is not enough energy in our civilization to move such mass, even if it existed in a convenient location. The gravity of a planet is written into its fundamental nature at the moment of its formation. When Mars coalesced from the protoplanetary disk 4.5 billion years ago, its final mass was determined by the amount of material available in its orbital region and the gravitational dynamics of the young solar system. Jupiter's massive gravity likely prevented Mars from growing larger, starving it of the material it needed to become an Earth-sized world. What we have now is what we will always have. Mars is a small planet, and small planets have weak gravity. This unchangeable reality triggers a cascade of biological disasters that unfold slowly, invisibly, and relentlessly. The human body is not merely adapted to Earth's gravity. It is built by it, maintained by it, and defined by it. Every system, from the cellular level to the architectural structure of our skeleton, evolved under a constant 1g acceleration. Remove that force, or even reduce it significantly, and the body begins to change. Not immediately, not dramatically at first, but continuously, progressively, and possibly irreversibly. The early advocates for Mars colonization, the visionaries who inspired generations with images of red deserts dotted with pressurized domes and greenhouse gardens, often acknowledged gravity as a concern, but rarely as a deal-breaker. In the optimistic literature of the 1950s through the 1990s, Mars was presented as challenging but conquerable. The assumption, spoken or unspoken, was that humans are adaptable. We survived the Ice Age. We crossed oceans. We learned to fly. Surely we could learn to live in lower gravity. After all, the Apollo astronauts walked on the Moon, which has even less gravity than Mars, only 16% of Earth's pull, and they returned home healthy. But the Apollo missions lasted days, not years. The astronauts were not building civilizations. They were not having children. They were not asking their bodies to maintain Earth-normal function indefinitely, while being pulled at a third of the force that shaped human evolution. The International Space Station has taught us that what seems manageable in the short term becomes catastrophic over months and years, and the space station orbits in microgravity, near 0 G. Mars offers more gravity than the ISS, but the question haunting researchers today is whether 38% is enough. Is there a threshold below which the human body simply cannot maintain its structure? A minimum gravity requirement for long-term health? We do not yet know the answer. But every piece of evidence gathered from decades of spaceflight suggests that the answer may be no. That the gravity on Mars may fall below the threshold of human biological compatibility. That the red planet, for all its promise, all its ancient river valleys and polar ice, all its proximity and relative accessibility, may be fundamentally uninhabitable not because of what it lacks in atmosphere or water, but because of what it lacks in mass. The gravity crisis is not a problem we will solve with better technology. It is a reality we must accept, adapt to, or abandon our dreams of walking freely beneath Martian skies. As we prepare to explore what this means for the human body, we must confront an uncomfortable truth. The greatest obstacle to becoming a spacefaring civilization may not be the distance between worlds, but the difference in how strongly they pull us down. Before we can dream of walking on Martian soil, we must confront what decades of orbital research have revealed. The human body was never designed for worlds where gravity releases its grip. High above Earth, aboard the International Space Station, astronauts have served as unwitting test subjects in an experiment we did not fully understand when we began it. They float through modules with practiced grace, performing somersaults that would be impossible on Earth, their bodies adapting to an environment where up and down have lost all meaning. They smile for cameras, conduct experiments, and gaze at our planet suspended in the blackness below. But beneath the wonder, beneath the achievement, something profound is happening. Something we cannot see in the photographs. Their bodies are changing, not adapting, deteriorating. The ISS orbits in microgravity, a condition where the constant acceleration of freefall creates the sensation of weightlessness. Mars, by contrast, offers 38% of Earth's gravitational pull, a substantial difference from zero, yet still a world away from what our bodies have evolved to withstand. For billions of years, every ancestor we have ever had lived under the constant pull of Earth's gravity. Our bones grew dense to support our weight. Our hearts pumped with the strength needed to push blood upward against gravity's insistent tug. Our muscles developed the architecture to hold us upright, to move us forward, to resist the eternal downward force. Remove that force, even partially, and the body does not celebrate its newfound lightness. It begins to dismantle itself. The first warning sign appeared in the bones. Astronauts returning from extended missions in space showed bone density loss that shocked medical researchers. On Earth, bones constantly rebuild themselves through a delicate balance of creation and destruction. Cells called osteoblasts build new bone tissue, while osteoclasts break down old bone, a process regulated by the mechanical stress of bearing weight. In microgravity, that stress vanishes. The body, operating with ruthless efficiency, decides that dense, heavy bones are no longer necessary. It begins to cannibalize them. Studies reveal that astronauts lose between 1% and 2% of their bone mass per month in weightlessness, primarily in load-bearing bones, the spine, hips, and legs. This is not a temporary condition that reverses immediately upon return. Some astronauts never fully recover the bone density they lost, even years after landing. They return from space with the skeletal fragility of someone decades older. On Mars, with its partial gravity, we might expect the loss to be less severe. Perhaps it would be. But perhaps is not a foundation upon which to build a civilization. Early research suggests that even reduced gravity may trigger similar processes, just at a slower rate. The body does not distinguish between no gravity and not enough gravity with the precision we would hope. If Martian settlers lose even half the rate observed on the ISS, they would face catastrophic bone loss within a few years. A simple fall, the kind that might bruise an Earthling, could shatter a Martian's femur. A sneeze could crack ribs. The very act of living becomes a dance with fracture. Muscle follows a parallel descent. Without the constant resistance of gravity, muscles atrophy with startling speed. Astronauts can lose up to 20% of their muscle mass within a matter of months, particularly in the legs and back, the very muscles that define our upright existence. On the ISS, astronauts exercise rigorously for 2 hours every day, using specially designed equipment to simulate weight-bearing activities. Despite this intensive regimen, they still lose muscle. Their legs become thin, almost bird-like, while their faces swell from fluid redistribution, creating what scientists have dubbed the puffy face, bird legs syndrome. The human form, refined over millions of years, begins to reshape itself into something alien. On Mars, colonists would face the same gradual weakening. The difference is they would never come home. They would exercise daily, perhaps for hours, fighting against their own biology, knowing that the moment they stop, the deterioration accelerates. It is not exercise for fitness, it is exercise for survival. The cardiovascular system tells perhaps the most troubling story. On Earth, your heart works constantly against gravity, pumping blood upward to your brain, maintaining pressure throughout your body. In space, this effort becomes unnecessary. The heart, like the bones and muscles, begins to adapt. It becomes smaller, weaker. Blood volume decreases as the body decides it no longer needs as much. Astronauts experience orthostatic intolerance, a condition where standing upright after spaceflight causes dizziness, fainting, and dangerously low blood pressure. Their cardiovascular systems have forgotten how to function under gravity's rule. Some astronauts cannot stand for more than a few minutes immediately after landing. Medical teams must help them from their capsules like invalids. These are individuals who were among the fittest humans on Earth before launch, athletes in peak condition. Space has undone them. If Martian colonists ever attempted to return to Earth after years in low gravity, their hearts might not be capable of sustaining them here. The journey home could be a death sentence, not from the voyage itself, but from the simple act of arriving. Even on Mars, a weakened cardiovascular system means reduced endurance, increased fatigue, and heightened risk of cardiac events. The heart is not a muscle that can be easily strengthened with exercise when the fundamental environment does not demand its full capacity. Then there are the eyes. Spaceflight-associated neuroocular syndrome, known as SANS, was discovered almost by accident when astronauts began reporting vision changes during and after long-duration missions. Without gravity pulling fluids downward, cerebrospinal fluid accumulates around the brain, increasing intracranial pressure. This pressure deforms the eyeball, flattens the back of the eye, and can cause swelling of the optic nerve. Some astronauts have developed permanent vision impairment. They left Earth with perfect eyesight and returned needing glasses, not from aging, but from the physical restructuring of their eyes. On Mars, with its partial gravity, would this pressure be relieved? Perhaps partially, perhaps not at all. We do not know. SANS remains one of the most mysterious and concerning effects of spaceflight, and we have no guaranteed solution. The immune system, too, shows signs of collapse. Studies of astronauts reveal that their immune response becomes suppressed in space. White blood cell function decreases. Dormant viruses that have been held in check for years suddenly reactivate. Inflammation increases throughout the body, accelerating aging at the cellular level. Wounds heal more slowly. Infections become more dangerous. The body's ability to defend itself diminishes just when it is most vulnerable, living in an artificial habitat far from Earth's hospitals and medical infrastructure. On Mars, even a minor infection could escalate into a crisis. A scraped knee could become life-threatening. The colonists would be constantly at war with their own compromised biology. All of these changes, documented meticulously through decades of ISS operations, represent our most complete picture of what happens to human bodies beyond Earth. Yet the ISS is a laboratory in microgravity, not low gravity. We do not have perfect data for Mars because no human has ever lived in 0.38 G for extended periods. We are extrapolating, estimating, hoping that the partial gravity of Mars will provide enough protection to slow or prevent some of these effects. But hope is not science. Estimation is not certainty. And the cost of being wrong is measured in human suffering. Astronauts on the ISS know they are coming home. They endure the bone loss, the muscle atrophy, the vision changes because they understand it is temporary. Months in space, then back to Earth for recovery. Martian colonists would have no such comfort. Every day on Mars would bring more deterioration. Every week would mark another step away from the body they once had. They would feel themselves weakening, year by year, becoming something less than they were, adapted to a world that is not quite enough to sustain what they were designed to be. The ISS has given us an invaluable gift, a warning. It has shown us that the human body is exquisitely tuned to Earth's gravity, and that removing or reducing that force triggers cascading failures across multiple systems. We now face a choice. Do we acknowledge these warnings and adjust our plans accordingly, Or do we push forward, hoping that Martian gravity will be different enough to spare us from the worst? The ISS floats above us, a monument to human achievement and a testament to biological fragility. Its lessons are written in the bones of every astronaut who has lived there. The question is whether we are willing to read them. As we contemplate the establishment of permanent colonies on Mars, we arrive at perhaps the most profound and unsettling question of all. What happens when the first child is born beneath the rust-colored sky? This is not a question of technology or engineering. It is a question that reaches into the very essence of what it means to be human, and whether humanity itself will diverge into separate branches, divided not by oceans or continents, but by the fundamental force of gravity itself. The first generation of Martian settlers will be volunteers, people who choose to accept the risks, who willingly trade Earth's comforting embrace for the adventure of a new world. But their children will have no such choice. Born into a gravitational field just 38% that of Earth, these children would develop in ways we can barely predict, their bodies adapting to conditions that have never shaped human biology in our entire evolutionary history. Every bone, every muscle, every organ would form under the influence of Martian gravity, creating humans who may be fundamentally different from their Earth-born parents. The process begins in the womb. On Earth, a developing fetus experiences constant pressure, the weight of amniotic fluid, the mother's movements, the pull of gravity itself, all contributing to the formation of bones and muscles designed to function in 1G. But what happens when that gravitational force is reduced by more than half? We simply do not know. No human has ever been conceived, gestated, or born beyond Earth's surface. The few studies conducted on animal reproduction in space reveal outcomes that range from concerning to catastrophic. Experiments with pregnant rats aboard spacecraft have shown disturbing results. Some embryos failed to develop properly. Others exhibited malformations of the skeletal system. In the microgravity of low Earth orbit, the fundamental processes of cell division and tissue formation appear to be disrupted in ways that scientists are only beginning to understand. While Mars offers more gravity than orbital space stations, it may not offer enough. The development of weight-bearing bones requires mechanical stress, pressure, resistance. Without sufficient gravitational load, will a Martian fetus develop the bone density needed to ever stand on Earth? Consider the implications as the pregnancy progresses. The mother's body, already weakened by months or years in low gravity, must now support the growth of another human being. Her bones are leaching calcium. Her muscles have atrophied. Her cardiovascular system has adapted to pumping blood in an environment where standing and sitting create far less pressure differential than on Earth. Pregnancy itself is physically demanding even in optimal conditions. On Mars, it could become a medical crisis, one that tests the limits of both mother and child, and then the child is born. Those first moments, the first breaths of thin, artificially pressurized air, mark the beginning of a life unlike any that has come before. This child will learn to walk in 38% gravity, developing a gait and muscle structure optimized for Mars. Their bones will grow denser where Martian gravity demands it, but perhaps never achieve the density that Earth-born humans possess. Their heart will beat in a rhythm calibrated to a lighter body, pumping blood through vessels that have never known the full weight of terrestrial existence. In every measurable way, this child is adapting to Mars, becoming something new. The terrifying question emerges as the child grows. Could they ever return to Earth? Imagine a 10-year-old born on Mars, stepping off a spacecraft onto Earth for the first time. The moment their feet touch the ground, they would experience nearly 3 times the gravitational force their body has ever known. Their legs, strong enough to run across Martian plains, might buckle under their own weight. Their spine, perfectly adequate for supporting their frame on Mars, could compress dangerously under Earth's pull. Their heart, accustomed to the gentle demands of low gravity, would suddenly need to pump blood upward against a force it was never designed to overcome. We have already seen what happens to Earth-adapted humans after just months in low gravity. Astronauts return weak, disoriented, struggling with the simplest movements. Now imagine a human who has spent not months but years, or an entire lifetime in reduced gravity. The return might not just be difficult, it might be impossible. These children of Mars could be prisoners of their birth world, forever unable to visit the planet that gave rise to their species. They would look at images of Earth's oceans, forests and mountains, knowing they can never walk upon them, that the cradle of humanity is now an alien world to them, as hostile as Mars once was to their ancestors. The ethical dimensions of this reality are staggering. Is it moral to bring children into existence knowing they may never have the choice to leave? On Earth, we generally accept that children are born into circumstances they do not choose: nations, economic conditions, geographic locations. But there has always been the theoretical possibility of movement, of migration, of seeking different conditions. A child born on Mars may have no such possibility. They would be bound to that world not by laws or borders, but by the immutable laws of physics, by the limitations of their own biology. Some might argue that this is simply the price of expansion, that pioneers have always raised children in harsh frontiers, knowing those children might never return to the homeland. But this is different. This is not about distance or convenience. This is about creating humans whose fundamental physiology makes them incompatible with the world their species evolved to inhabit. We would be witnessing, in real time, the beginning of a speciation event, the point where humanity begins to diverge into separate lineages. Homo sapiens terrestris and Homo sapiens martialis perhaps, each adapted to their respective worlds, each increasingly unable to survive in the other's domain. The implications extend beyond individual lives. Over generations, if a Martian population becomes truly self-sustaining, we could see the emergence of distinct human variants, shaped by environmental pressures that operate on timescales we can barely comprehend. Martian humans might develop longer limbs, more efficient lungs adapted to lower atmospheric pressure, perhaps even changes in facial structure or organ placement optimized for their environment. These would not be surgical modifications or genetic engineering, though those might accelerate the process, but natural adaptation over countless generations. The family tree of humanity would branch, and those branches might never rejoin. Perhaps most haunting is the possibility that these children would not see themselves as diminished or imprisoned. To them, Mars would be home, the natural state of existence. Earth would be the strange world, the heavy planet where everything weighs too much and the sky is the wrong color. They might look at their earthborn parents with a mixture of curiosity and pity, unable to fully understand why anyone would choose to live under such crushing gravitational oppression. The divide would not just be physical, but psychological, cultural, perhaps even philosophical. What does it mean to be human when humans exist in fundamentally different physical realities? The first child born on Mars will be celebrated as a milestone, a triumph of human expansion into the cosmos. But in that celebration, we must not lose sight of what we are truly creating. A new branch of humanity, one that may never touch Earth's soil, never feel ocean waves, never know the weight of their true ancestral home. The children of Mars will inherit not just a new world, but a new form of existence, one that comes with extraordinary possibilities and equally extraordinary limitations. In reaching for the stars, we may discover that the price of expansion is nothing less than the transformation of humanity itself. When humanity first recognized the gravity problem on Mars, the engineers did what engineers do best. They began to design solutions: rotating habitats, centrifuges, weighted suits, pharmaceutical cocktails, magnetic systems that could simulate weight. On paper, in computer simulations, and in the imaginations of brilliant minds, these solutions appeared elegant, achievable, even inevitable. But as we examine each proposal more closely, a troubling pattern emerges. Not one of them truly solves the problem. Some are impractical, others are incomplete, and many require resources so vast, energy so immense, that they transform Mars colonization from a challenge into an impossibility. The most frequently proposed solution is the rotating habitat, a structure that spins to create artificial gravity through centrifugal force. The concept is simple and rooted in physics we understand completely. Spin a cylinder fast enough, and objects inside will press against the outer wall, simulating the pull of gravity. Science fiction has immortalized these designs. O'Neill cylinders stretching miles into space, Stanford Taurus stations rotating like cosmic wheels, Babylon 5, The Expanse, Elysium. These visions are beautiful and theoretically sound, but they share a fatal flaw. They work only in space, not on a planet. Mars is not empty void. It is a world with terrain, with dust storms, with a thin atmosphere that resists motion. Building a rotating habitat on Mars requires constructing massive structures that can spin continuously without friction. without failure, and without the degradation that comes from constant mechanical stress. The engineering tolerances are extraordinary. If the rotation is too fast, inhabitants experience severe motion sickness and disorienting Coriolis effects. Every movement becomes curved. Throwing an object feels wrong. Walking becomes a learned skill, relearned daily. If the rotation is too slow, the artificial gravity is too weak to provide benefit. The habitable zone narrows to a razor's edge. To create artificial gravity equivalent to Earth's pull, a rotating cylinder must be enormous. A small habitat, say 100 feet in diameter, would need to spin so rapidly that the Coriolis forces would make it uninhabitable. The minimum comfortable diameter for a rotating structure is estimated at roughly 200 meters, nearly 2 football fields across. Larger is better. The Stanford Torus design envisions a wheel nearly a mile in diameter. An O'Neill cylinder would stretch for miles, containing entire ecosystems within its curved interior. These are not buildings. They are megastructures requiring materials, precision manufacturing, and energy expenditure beyond anything humanity has yet attempted. On Mars, where every gram of material must be transported millions of miles or extracted from hostile terrain, the cost becomes astronomical. And even if we built such a structure, it would serve only those inside it. Step outside to explore the planet, to mine resources, to conduct research, and you return to Martian gravity. The colonists would exist in a perpetual state of transition, their bodies never fully adapting to either environment. Studies on Earth show that frequent transitions between gravitational states cause greater physiological stress than consistent exposure to one environment. The human body craves equilibrium. A rotating habitat does not provide it. It offers only temporary respite. Some propose smaller solutions. Personal centrifuges where colonists would spend hours each day, strapped into spinning devices that press them against padded walls, simulating gravity for their bones and cardiovascular systems. These exist already on Earth, used in experimental settings and by some space agencies for astronaut conditioning. But the results are mixed at best. Hours of daily centrifuge time can slow bone loss but not stop it. The treatment is exhausting, nauseating, and mind-numbingly monotonous. Imagine dedicating 3 to 4 hours every single day, for the rest of your life, strapped into a spinning chamber, your body pressed uncomfortably against padding, experiencing artificial weight that feels nothing like natural gravity. This is not living. This is medical treatment masquerading as a solution. Then there are weighted suits, exoskeletons designed to add mass to the body, forcing muscles and bones to work harder in low gravity. The theory suggests that if you increase the load, you can compensate for the reduced gravitational pull. Athletes on Earth use weighted vests during training. Why not apply the same principle on Mars? The answer lies in understanding what gravity truly does. Gravity is not simply weight pressing down on your skeleton. It is a constant, omnipresent force acting on every cell, every fluid, every system in your body simultaneously. Weighted suits add external load, but they cannot replicate the internal pressure gradients that gravity creates. Your cardiovascular system does not work harder simply because you are wearing a heavy backpack. Your bones do not receive the precise mechanical signals they evolved to interpret. The weighted suit becomes another incomplete answer, a band-aid on a wound that requires surgery. Exercise regimens have been refined for decades aboard the International Space Station. Astronauts spend 2 to 3 hours daily on treadmills, resistance machines, and specialized equipment designed to stress their muscles and bones. Despite this rigorous commitment, they still lose bone density, still experience muscle atrophy, still return to Earth weakened. The exercise slows the degradation but does not prevent it. On Mars, with 38% of Earth's gravity providing some baseline resistance, the degradation might be slower still, but it would not stop. You cannot simply work out more and overcome a fundamental physical reality. Gravity affects processes at the cellular level, influencing how bones remodel themselves, how stem cells differentiate, how your inner ear maintains balance. These are not problems that can be solved with more repetitions or heavier weights. Pharmaceutical interventions offer another avenue. Drugs like bisphosphonates, currently used to treat osteoporosis on Earth, can slow bone resorption. Researchers are exploring compounds that might stimulate bone growth even in low-gravity environments. But these medications come with side effects, some severe. Long-term use can cause jawbone deterioration, kidney problems, and increased fracture risk in certain bones. Taking medication daily for your entire life to counteract an environmental condition is not a solution. It is chronic management of a chronic problem. And we do not yet know if these drugs can fully compensate for the absence of gravity's constant mechanical stimulus. Then there are the more speculative concepts. Magnetic boots that could artificially pull a person downward, simulating weight through electromagnetic force. This idea sounds promising until you calculate the energy requirements. To generate enough magnetic force to simulate Earth gravity for a single person would require immense power and would only work on ferromagnetic surfaces. The colonist could never step on soil, rock, or ice without losing the effect. Magnetic flaws throughout an entire settlement would demand continuous energy expenditure so great it would drain resources needed for life support, food production, and essential operations. Each proposed solution requires energy, massive, continuous, unrelenting energy. Mars receives less than half the sunlight of Earth. Its winds are too thin to drive turbines efficiently. Nuclear power could provide baseline needs, but every watt dedicated to artificial gravity systems is a watt not available for heating, oxygen generation, or communication. The resource cost compounds with every additional colonist, every expanded habitat, every new facility. Engineering solutions that might work for a small research station of a dozen people become unmanageable for a colony of hundreds or thousands. The truth that emerges from examining these solutions is uncomfortable. We are not limited by imagination or even by technology. We are limited by physics and practicality. Gravity is not a feature we can add through clever engineering. It is a fundamental property of planetary mass, and Mars simply does not have enough of it. Every solution we propose is partial, temporary, or prohibitively expensive. None address the core reality. On Mars, your body will be in a constant state of decay, and no amount of spinning, lifting, or medicating will fully restore what gravity provides freely on Earth. There is a particular kind of suffering that arrives slowly, not with the violence of a single catastrophic event, but through the quiet accumulation of losses too small to name individually, yet devastating when summed across months and years. This is the psychological reality awaiting those who choose to live on Mars, not the adventure they imagined, not the heroic narrative of planetary pioneers, but something far more intimate and insidious. The experience of inhabiting a body that is gradually failing, and knowing with absolute certainty that it will continue to fail as long as they remain. Imagine waking each morning to discover that your body has become slightly more of a stranger. Your bones ache with a deep, persistent throb that no medication fully silences. This is not the sharp pain of injury, which the mind can contextualize and expect to heal. This is chronic pain, the kind that disability researchers describe as fundamentally altering one's relationship with existence itself. On Mars, bone density loss occurs at roughly 1 to 2% per month. Over a year, a colonist might lose 12 to 24% of their skeletal mass. The vertebrae compress, the hips weaken. Simple movements that once required no thought, standing from a chair, climbing stairs, become calculated risks. The body begins to feel less like a home and more like a prison with walls that close inward day by day. Muscle atrophy compounds the nightmare. Despite rigorous exercise regimens, despite hours spent fighting against machines designed to simulate resistance, the muscles waste. Legs that once carried you across Earth now tremble under Mars's lighter load, not because the gravity is too strong, but because the body, deprived of the constant challenge Earth's gravity provided, has begun to cannibalize itself. Astronauts on the ISS report that after months in microgravity, their legs feel alien, disconnected. On Mars, the sensation is slower, but no less profound. The body you see in the mirror becomes unfamiliar, gaunt, weakened, transformed by forces you cannot control. But perhaps the deepest wound is not physical at all. It is the psychological fracture that occurs when you realize this deterioration is not temporary. On Earth, illness and injury exist within a framework of potential recovery. We endure pain because we believe it will end. On Mars, there is no recovery, only management. Every colonist knows intellectually what they signed up for, but knowing something intellectually and living it emotionally are separated by an abyss. Psychologists studying chronic illness have identified a phenomenon they call perpetual loss. It is the grinding awareness that your baseline is not stable, that tomorrow you will be weaker than today, that next year you will be weaker still. This is not adaptation. This is a slow-motion catastrophe of identity. The social dimensions amplify the isolation. Disability studies have long explored how bodily difference shapes human experience, how societies construct normalcy, and marginalize those who fall outside it. On Mars, an entire population would exist in a state of progressive disability by Earth standards. But unlike disability communities on Earth, which have built rich cultures, support networks, and frameworks for dignity and meaning, Martian colonists would face something unprecedented. A shared knowledge that their condition is both irreversible and alienating them from the rest of humanity. Every video call home becomes a reminder. Family members on Earth age, but they remain fundamentally human in form. Martian colonists age differently, their bodies reshaping according to alien physics. The divergence is not just physical, it is existential. Children born on Mars, whose bones form in low gravity from the start, may never experience this particular anguish. But for those who remember Earth, who carry in their cellular memory what it felt like to stand under a gravity that held them firmly, the loss is profound. Some researchers have suggested that Mars colonists may develop entirely new psychological conditions, syndromes without Earth-based equivalents. Imagine a form of phantom limb syndrome, but instead of mourning a lost arm or leg, you mourn your entire former relationship with gravity, with strength, with the simple joy of movement. We might call it gravitational dysphoria or planetary homesickness, though no term yet invented can capture the totality of the experience. And then there is the knowledge, growing heavier with each passing month, that return to Earth is becoming less viable. In the first year, perhaps the body could readapt with intensive rehabilitation. After 2 years, the risk of cardiovascular collapse upon return grows significant. After 5 years, some researchers believe the human body may cross a threshold beyond which Earth's gravity becomes genuinely dangerous, even lethal. This is not conjecture designed to frighten, it is extrapolation from decades of data on astronauts returning from space. The isolation of Mars is not merely spatial, it is temporal, a one-way drift away from the world that made you. Quality of life research asks fundamental questions. What makes existence meaningful? What level of suffering negates the value of experience? These are not abstract philosophical exercises for Martian colonists. They are daily negotiations. Is the adventure of living on another world worth the chronic pain? Is contributing to humanity's expansion worth watching your children grow up in bodies that could never survive the homeworld of their species? There are no universal answers. Some may find profound meaning in sacrifice. Others may discover that the cost extracts more than they had to give. Living on Mars, then, is not simply a physical challenge to be overcome with technology and determination. It is a confrontation with the limits of human resilience, a test of whether consciousness can find peace in a body that evolution never prepared for the environment it now inhabits. The psychological toll is not a side effect of Martian colonization. It is perhaps the central experience, the defining reality that every colonist will carry, heavier than any equipment, more persistent than any dust storm. In the end, we must ask not whether humans can survive on Mars, but whether they can thrive while slowly coming apart, and whether the human spirit can endure not just the darkness of space, but the darkness of watching yourself fade, molecule by molecule, into something no longer quite built for any world at all. Mars sits in a strange place in our imagination. It feels like the obvious choice, close enough to reach in a human lifetime. Solid ground beneath your feet, ice in the soil. Carbon dioxide in the air to turn into fuel and oxygen. Sunlight, seasons, days only slightly longer than Earth's. If you were designing a second home for humanity from scratch, you might sketch something that looks a lot like Mars. And yet, hidden inside that almost perfect design is the one parameter we never got to negotiate. Gravity, 38%. Not half, not 3/4. Little more than 1/3. It is the number that quietly turns Mars from best candidate into a biological trap. To understand how cruel that number is, we have to compare it to our other options. Not the Mars in our dreams, but the rest of the real estate the solar system has put on the market. Turn inward, toward the sun, past the scorched silence of Mercury, past Earth's blue, to a world we usually dismiss as hell, Venus. On the surface, Venus is a nightmare. Temperatures hot enough to melt lead, pressures that would crush a submarine, clouds of sulfuric acid. It is a planet that seems to actively reject the idea of human presence. But a few dozen kilometers above that inferno, something remarkable happens. There is a layer in Venus's atmosphere where the pressure is close to 1 atmosphere, where the temperature, while still hot, is survivable with the right materials. And there, floating in the orange light, the pull of Venus is almost exactly the same as Earth's. A human body in a Venusian cloud city would weigh what it weighs on Earth. Bones would feel the same constant load. Fluids would settle with the same familiar tug. The inner ear, that delicate accelerometer built into our skulls, would whisper the same message it has whispered for millions of years. Down is this way. You belong here. No one is suggesting that building floating cities in acid clouds is simple. The engineering demands are staggering. Buoyant habitats larger than skyscrapers. Materials that can survive corrosive droplets and constant wind. Launch pads suspended in the air, with no solid ground below. It is a concept that lives, for now, in art, in speculative papers, in the quiet musings of engineers late at night. But gravity, the one factor we cannot negotiate with, is on our side there. Venus challenges us with heat, chemistry, and engineering. Those problems are terrifying, but they are straightforward in one crucial way. They sit outside our skin. They can be met with alloys and polymers and cooling loops. They can be walled off. Venus tries to destroy our machines. Mars, with its gentle fall and endless horizon, quietly tries to destroy us. Look the other way now, outward, toward our own familiar companion, the Moon. We have walked there. We have left flags and footprints and dusty tracks from electric rovers. It is the first place most space agencies mention when they talk about returning to deep space. But the Moon pulls even less on us than Mars does. 16.5% of Earth's gravity. If you weigh 180 pounds on Earth, you weigh about 30 on the Moon. To your eyes, it would feel like slow-motion freedom. To your cells, it would feel like an insult. Bones would shed calcium even faster. Muscles would atrophy with even less resistance to push against. The heart would not need to fight so hard to lift blood. It would grow weaker, retuned to a world that asks less of it. So why do we still talk seriously about lunar bases? Because the Moon is close, 3 days away, not 6 months, not a year and a half. In lunar gravity, your body might start to fail, but an evacuation is a single burn and a few orbits away. A lunar base can be a laboratory for low-gravity medicine, a test bed for the very therapies Mars would require. But with an escape route. On Mars, low gravity is a sentence. On the Moon, it can be an experiment. Farther out, scattered between Mars and Jupiter, lie the asteroids. They whisper promises of metals, water, rare elements. These are the quarries and fuel depots of a spacefaring civilization. They are also almost weightless. On many asteroids, you do not walk. You push off and drift. A strong jump can liberate you from the rock entirely. Microgravity is not just low gravity. It is the almost total absence of down. No one seriously imagines cities on these tumbling boulders, not in the way we imagine cities on Mars. Asteroids are for robots, for miners in exoskeletons, for outposts measured in weeks or months, not generations. They teach us a simple lesson. Without gravity, you don't build a home, you build a work site. So if worlds are too heavy or too light, where does that leave us? It leads us to an idea that abandons planets altogether. Imagine an empty frame spinning in the dark. A ring, a cylinder, a vast wheel turning slowly against the stars. Inside its rim, flaws curve overhead until they become walls and then ceiling. You walk down toward the outer edge, feeling a familiar pull under your feet. There is no planet at the center of this world, only space, yet your body cannot tell the difference. O'Neill cylinders and other rotating habitats solve the one problem Mars cannot. They give us the gravity we evolved for. Not a compromise, not a third, not a sixth. 1G tuned by rotation like the tempo of a song. The physics is disarmingly simple. Spin a structure. Let centrifugal force press its inhabitants outward. The faster it spins and the wider it is, the more the outward push can mimic gravity. Inside, bones feel properly loaded. Fluids settle. The heart struggles. Just enough. Here, gravity is no longer a gift of formation. It is an engineering choice. But this elegant solution comes with its own equally stark irony. A spinning cylinder in deep space has nearly perfect gravity and no resources. No air, no water, no metals, no ice. It is by itself nothing but a shell. Mars, in contrast, is rich. It offers ice at the poles and in the soil, regolith full of oxygen-bearing minerals, carbon dioxide to turn into fuel. It is a warehouse of everything you'd want to fill a space habitat with. Mars has the resources but the wrong gravity. Space habitats can have the right gravity but need the resources Mars holds. It is as if the solar system has split the recipe for a habitable world into two separate places and challenged us to bridge the gap. We can imagine a future where we do just that. Robotic freighters lifting metals and volatiles from Mars or its moons, feeding a growing archipelago of spinning habitats in orbit. Mars as a mine and manufacturing hub. The real cities of humanity not on its dust but circling above it where our biology can be kept whole. This is the tragic twist in Mars's story. For over a century we saw it as a second Earth, a place where we might breathe, farm, raise children under a smaller, paler sun. We obsessed over atmospheres, temperatures, radiation, soil chemistry. We drew domes and greenhouses and pressurized rovers. Gravity was a footnote. Now, as this quiet force steps into the spotlight, the hierarchy of what matters shifts. Radiation can be blocked with rock and water. Atmospheres can be thickened. Temperatures can be managed with power and insulation. These are engineering problems, daunting but familiar. Gravity is not a shield we can stack. It is not a gas we can pump in. It is the shape of motion itself. To change it, we have to move worlds or move ourselves. Of all the factors we weighed when we crowned Mars our best candidate, gravity might be the one we understood the least, and the one that matters the most. Not because it's exotic, but because it is mundane. Because it acts everywhere, all the time, on every cell, silently instructing our bodies how to be human. Mars tempts us with everything we need to live, then quietly withholds the one thing we need to remain who we are. In that gap, between almost enough and just not quite, we find the true cost of our Martian dream. The journey to Mars is not just a question of distance, it is a question of deadlines. Not the kind marked on mission timelines or launch windows, but the quiet biological deadlines written into our bones, our hearts, and our blood. Every day away from Earth's gravity is a kind of clock. And somewhere along that ticking line, there may be a moment when you cross a threshold you can't uncross. A point where coming home stops being a logistical challenge and becomes a medical impossibility. On the International Space Station, this clock is already visible. If you know how to read it, an astronaut spends 6 months orbiting Earth at microgravity. To the eye, they look fine. They float gracefully, strap themselves to treadmills, smile for cameras. But the body is keeping score. Blood redistributes toward the head. The heart, no longer pumping against gravity, weakens and shrinks. Leg muscles atrophy. Balance systems in the inner ear begin to recalibrate to a world where up and down no longer exist. Bones quietly dissolve calcium into the bloodstream, as if the skeleton is no longer needed. The moment they return to Earth, the illusion of adaptation ends. Touchdown is not triumph, it's shock. Some astronauts cannot stand unaided when the capsule is opened. Their blood pressure crashes as gravity suddenly demands circulation downward again. The heart struggles. They feel dizzy, nauseous, weak. Months of training are needed to relearn what your body once did automatically. Walk, balance, climb stairs without fainting. After a typical 6-month ISS mission, rehabilitation can take months. Cardiovascular function, muscle mass, bone density. None of them snap back the instant Earth's gravity returns. The return itself is the most dangerous day of the mission. The body that adapted so elegantly to weightlessness finds itself suddenly obsolete on the planet that built it. This is with microgravity. For half a year, a few hundred kilometers away, with immediate emergency care available. Mars is not a few hundred kilometers away. To reach Mars with current or near-term technology takes roughly 6 to 9 months, depending on alignment and propulsion. Half a year of floating in effectively weightless space, followed by an abrupt arrival into a world that is itself only a shadow of Earth's gravity. About 38% of what your muscles and bones evolved for. Your body will begin adapting twice. First to microgravity on the journey out, then to Mars's low gravity on arrival. Each adaptation pushes you a little further from the physiology that can comfortably survive on Earth. Imagine the full arc. You leave Earth, 6 to 9 months in transit. Your heart weakens, your spine lengthens, your bones thin. You land on Mars. Now, your body is asked to function at 0.38 G. Harder than zero, but far easier than home. The heart still works less than it would on Earth. The skeleton still bears less load. Every day the signals going through your nervous system whisper the same instruction. This is the new normal. You don't need to be Earth-strong anymore. Stay for 500 days, a typical long-stay mission tied to orbital mechanics. and then face another 6 to 9 months back in microgravity on the return. By the time you see Earth again, your body will have spent years telling itself that gravity is optional. We have no long-duration human data in 0.38 G. We only have small numbers from microgravity and bedrest analogues, but we can trace the curve. After 6 months in microgravity, we already see serious deconditioning. After a year, the issues deepen. After multiple years, models predict profound cardiovascular remodeling, severe loss of bone density, up to 1–2% per month in some regions without aggressive countermeasures, and changes in how blood vessels regulate pressure. Now add reduced gravity on Mars. Not as brutal as weightlessness, but enough to keep the body from fully maintaining Earth-grade strength. The question is not whether you will adapt to Mars. You will. The question is whether that adaptation will push you across the invisible line where 1G becomes hostile territory. Cardiologists and space physiologists worry about what happens the day a long-term Martian colonist steps, or tries to step, back into Earth's gravity well. A weakened heart must suddenly pump against triple the weight it has grown used to. Blood that happily circulated in 0.38 G is now dragged relentlessly downward. Blood pressure in the legs surges, and in the brain it drops. The risk is not abstract. Fainting, organ underperfusion, arrhythmias, even cardiac arrest are not science fiction scenarios. They are known risks extrapolated to a harsher environment. For someone born or raised from childhood in Martian gravity, the problem deepens. Their bones may never mineralize to Earth standards. Their muscles might never develop the cross-sectional strength required here. Their cardiovascular system may calibrate its entire lifespan around 0.38 G. To them, a return to Earth would not be coming home. It would be stepping into a crushing field that their organs are not built to withstand. At some point, months, years, or a full generation into Martian life, there exists a boundary. Before it, return is dangerous but possible with extensive rehabilitation. Beyond it, return might be medically contraindicated, not recommended. Not safe. We don't yet know where that point lies. 6 months? 2 years? 10? A full childhood? The data is thin, the models uncertain, but the direction of the curve is clear, and it bends away from Earth. This is more than a physiological curiosity. It rewrites what it means to go to Mars. If extended stays risk creating people who physically cannot return, then a Martian colony is not just remote. It is biologically isolated. One-way tickets stop being a romantic metaphor and become a literal medical category. Insurance companies will notice. How do you underwrite a person who may, by design, become unable to return to the environment where most advanced medical care exists? Does a Martian resident count as permanently disabled by Earth standards, or simply differently enabled in 0.38 G? Medical ethics will strain. Can you approve a mission for a crew knowing that, based on current science, some of them may cross the threshold of safe return without a clear understanding of when that happens? Do you need informed consent that explicitly says, after X time on Mars, we cannot guarantee your life if you attempt to come back? Law will follow. Are Martian-born children Earth citizens if they can never physically stand on the soil of the country on their passport? Who is responsible if a returning colonist dies because their heart fails under 1G stress? The agency that sent them, the doctors who cleared them, or the individual who chose to risk the journey home? And beneath all of this lies a quieter, more personal dilemma. If you decide to build a life on Mars, you may be deciding something else without fully realizing it, that your body will slowly sign a contract your mind did not intend. That one day, perhaps without ceremony, you will pass the point of no return. You might still be able to talk to Earth, see it in the sky as a bright wandering star, watch the blue marble in high resolution from orbiters and satellites, but your body will belong to another world. In that future, going to Mars will no longer mean traveling to another planet. It will mean something far more profound, changing species not in genes, but in gravity. Becoming a human who can look back at Earth with longing and know that physically, decisively, irrevocably, you can never go home. If Mars refuses to bend to the human body, some argue we should bend the human body to Mars. When engineers run out of mechanical tricks to fake gravity, the conversation drifts into territory that feels less like aerospace and more like science fiction. But fiction has a habit of becoming a rough draft for the future. If spinning habitats and buried lava tubes can't fully protect us, the next question is almost inevitable. What if we changed ourselves instead of trying to change the planet? Imagine a child conceived under the peach-colored sky of Mars. From the very first cell division, every signal in their body is unfolding in a world where down is only 38% as strong as it is on Earth. Their bones, their heart, their inner ear, even their genes responding to stress and load are all being asked to solve a problem no human lineage has ever faced. Right now, we simply watch and worry. But some scientists ask a different question. What if we didn't just wait to see how the body breaks? What if we pre-programmed it to survive? CRISPR, the molecular scissors that let us cut and paste DNA, has already rewritten the genomes of plants, animals, and even human embryos in tightly controlled studies. On Earth, we talk about CRISPR in the context of curing diseases, sickle cell anemia, certain cancers, hereditary blindness. But the same tools, in theory, could be turned outward, away from illness, toward adaptation. In a low-gravity world, we might try to edit for denser bones from the start. There are rare humans on Earth with mutations that make their skeletons extraordinarily thick and resistant to fractures. People who break medical scanners because their bones absorb too much X-ray. A future Martian geneticist could look at those variants and say, copy this. Muscle fibers could be tuned to resist atrophy. Genes that sense mechanical load. How much force your muscles and tendons experience might be adjusted so they respond more aggressively in weaker gravity, building and maintaining tissue with far less stimulus than Earth requires. Even the cardiovascular system could be redesigned. In low gravity, blood doesn't settle in the legs. It floats upward, pooling in the chest and head. Over time, the heart shrinks because it doesn't have to work as hard. An edited Martian heart might be wired to resist that downsizing, or even to overcompensate, staying stronger and thicker despite the easy workload. None of this is remotely simple. Biology is not a menu. Many genes have multiple roles, and a change that helps bone density might also increase cancer risk, alter brain chemistry, or shorten lifespan. The genome is less like a blueprint and more like a symphony. You can't just make the violins louder without changing how the entire piece feels. But transhumanist thinkers argue that this is not a bug, it is the point. Transhumanism is the philosophy that humans need not be the endpoint of evolution. Rather than clinging to a fixed definition of human, it welcomes transformation. Genetic, cybernetic, digital. As a natural next chapter, for a transhumanist, Mars is not a hostile mistake, it is an invitation. Gravity decreases. Radiation increases. The atmosphere thins. In response, we change. Instead of asking, how do we stay the same on Mars? They ask, what will a Martian be? This future Martian might not rely only on genes. Flesh alone may be too fragile. Cybernetic enhancements, machines woven into biology, offer a second path of adaptation. Imagine spinal implants that constantly sense bone loss and electrically stimulate nerves and muscles to counteract it, like an internal gym that never sleeps. Or micropumps assisting the heart, adjusting blood flow as you move between habitats with slightly different gravity levels or pressures. Exoskeletons could start as external support suits, helping settlers maintain muscle mass and joint alignment in low-gravity environments. Over time, those exoskeletons might shrink and migrate under the skin, becoming a mesh of smart fibers anchored to bone, sharing the mechanical load, part skeleton, part machine. Neural implants might help the brain recalibrate balance and orientation in a world where up and down feel almost negotiable. Today, we use cochlear implants to restore hearing and deep brain stimulators to treat Parkinson's disease. Tomorrow, a Martian child could grow up with a tiny device that constantly trains their vestibular system to interpret Mars's softer pull as normal. Taken far enough, this path leads to a being that is as much engineered as evolved. A body tuned for thin air, low gravity, high radiation, and perpetual dust. A form that might struggle on Earth's surface, the same way a deep-sea creature cannot survive on land. This raises a question that sounds philosophical but becomes painfully practical. At what point is a modified human no longer Homo sapiens? If we edit a handful of genes for bone and muscle, we are still comfortably within the blurry edges of our species. But what if Martian colonists accumulate thousands of alterations over generations? What if machine components become inheritable in practice, because a child's viable life on Mars requires them from birth? We already divide life into species using clumsy rules. Can two animals interbreed? Do their offspring remain fertile? In a future where Martians and Earthlings carry radically different genetic architectures, that test might fail. A couple from Mars and Earth might need advanced reproductive technology just to have a child without catastrophic incompatibilities. On paper, the label could change, from Homo sapiens to Homo Martis, or something stranger. In reality, the deeper issue is identity. Would Earth see Martians as fully human? Would Martians see us as frail, unfinished prototypes who never completed our evolution? None of this can happen without confronting ethics that are as heavy as Earth's gravity. To adapt a born adult who chooses cybernetic limbs or gene therapy is one thing. But many of the most powerful interventions for Mars, those protecting bone, heart, and brain from developmental harm, would likely need to occur before birth or very early in childhood. An embryo cannot consent to being redesigned for a planet it has never seen. A Martian teenager realizing they can never safely visit Earth, never stand in a true 1G field without risk, never run in rain under a thick blue sky, cannot undo those edits. Their fate would have been decided by people who believed a second world was worth the price of a second kind of human. Some ethicists argue this is no different than any child born anywhere. None of us choose our genes, our language, or our gravity well. Others respond that this is different. Here we would be choosing to introduce fundamental, irreversible changes not just for one child, but for an entire off-world lineage. It is the difference between being handed a random genetic deck and having that deck heavily edited for someone else's long-term project. And even if we set ethics aside, there is the clock. Our tools today, CRISPR base editors, prime editors, are powerful but crude. We can fix single letters of DNA, sometimes entire genes, but we do not yet command the complex networks that produce traits like resistance to low-gravity bone loss or lifelong cardiovascular stability on Mars. Designing and testing such changes safely would take not just years, but generations of careful research. The timeline for reliable, large-scale human genetic adaptation to a new world is measured not in mission cycles, but in centuries. Cybernetics may move faster, but integrating machines into the body at the level required for true planetary adaptation is also decades away. At minimum, Mars will not wait. Radiation will not pause. Low gravity will not negotiate. So we stand at an uncomfortable threshold. On one side, the fragile human body, evolved for a single world. On the other, the promise and the threat of redesigning ourselves into something tougher, stranger, and perhaps no longer fully recognizable. If we choose Mars and choose to stay, this debate is not optional. It is embedded in every airlock, every nursery, every grave dug into the red dust. Because the longer we remain on a planet that does not match our design, the more pressure there will be to change the design. And if we hesitate to cross that line, another idea waits in the shadows. Perhaps it is not humans who should become more like Mars. Perhaps it is Mars that must be remade, or abandoned to machines that do not care about gravity at all. Perhaps we have been thinking about Mars the wrong way, not as a new Earth, not as a backup civilization, but as something far more modest and far more honest. A research outpost, a rotating frontier, a place we visit, not a place we own. In this vision, Mars becomes less like a new continent and more like Antarctica. Nobody moves to the South Pole. They deploy. They rotate in for months, maybe a year, then come home before the environment breaks them down. The station remains. The people change. A Martian base could follow the same rhythm. Crews arrive, already conditioned with artificial gravity training in orbit. They conduct experiments, maintain equipment, explore nearby terrain. And then, before low gravity and radiation do irreversible harm, they leave. Another crew takes their place. The base is continuous. The humans are temporary. Instead of a city of 1 million Martians, imagine a population of a few dozen, constantly refreshed. Mars becomes a laboratory, not a homeland. In this model, time on Mars is not counted in generations, but in tours of duty. But this leads to an uncomfortable question. If Mars is too dangerous for permanent life, how much of that work needs us there at all? As our technology advances, the line between human explorer and robotic proxy begins to blur. Already, robotic missions have done what no human has yet achieved. Vikings, spirit, opportunity, curiosity, perseverance. They landed, survived, and did science for years in conditions that would slowly dismantle a human body. They do not suffer bone loss. They do not miss home. They do not need pressurized habitats or food shipments or protection from psychological isolation. And they are getting smarter. Imagine a new generation of Martian explorers. Not simple rovers creeping over rocks, but semi-autonomous machines with dexterous arms, precise instruments, and artificial intelligence that can adapt to unexpected events. They could map lava tubes, drill kilometers into the crust, assemble structures, and even build the habitats humans might one day use, without risking a single human heartbeat. From Earth, operators could guide them with a delay of just a few minutes. From orbit around Mars, a small crew could supervise an entire robotic workforce in real time, issuing commands, adjusting plans, troubleshooting problems. Human minds would still drive the mission. Human curiosity would still choose the questions. But human bodies wouldn't have to absorb the full cost of Martian gravity. This is the hybrid approach. Short-term human presence, long-term robotic persistence. A few people in Mars orbit or in heavily shielded, well-designed surface bases, supported by swarms of autonomous systems. Drones that fly thin Martian skies, burrowing robots that study layers of ancient sediments. Construction units that 3D print shelter from Martian regolith. Medical bots that monitor every heartbeat and radiation count, warning when it's time to go home. In this future, humans become directors rather than actors. We do not climb every hill ourselves. We choreograph a ballet of machines that can move faster, last longer, and survive more than we ever could. We choose when to step into the landscape, when a moment is so important that a human footprint is worth the risk. But even in this careful, balanced scenario, a temptation looms in the background. Terraforming, the dream that we could change Mars itself, thicken its atmosphere, warm its surface, release hidden water, seed its plains with life, turn a red desert into a blue-green world. Terraforming is a grand, audacious idea. It may someday change how we think about planetary engineering, about our relationship with entire worlds. But it has a limit that no amount of technology can pass. Terraforming can alter air. It can change temperature. It can sculpt rivers and oceans. It cannot change gravity, even if we wrapped Mars in a breathable atmosphere, filled its basins with liquid water, and painted its sky a hazy blue at sunset. Its pull would remain the same, about 38% of Earth's. Your bones would still weaken. Your muscles would still shrink. Children born there would still be built for that lighter world, and perhaps trapped by it forever. A perfectly terraformed Mars might look like paradise, while quietly dissolving the bodies of those who call it home. This reveals a deeper question, one that sits at the heart of our ambitions. Is human presence required, or just human intelligence? Does a world count as explored only when a human boot presses into its dust? Or is it enough that a human mind designed the mission, asked the right questions, interpreted the data, felt wonder at the results? If an AI-driven rover climbs Olympus Mons and sends back every rock angle, every spectral reading, every sound of Martian wind, did we go there? Or did we merely extend our senses outward, remaining safely inside the cradle of Earth's gravity? Some argue that without human presence, exploration is incomplete, that there is something irreplaceable about a human eye seeing an alien horizon in real time, a human hand brushing away the dust from a stone that has waited billions of years. That presence changes not just knowledge but meaning. Others suggest that clinging to physical presence is a kind of nostalgia. In a universe so vast and hostile, perhaps the future of exploration is not in our flesh, but in our extensions. Robotic bodies, synthetic minds, remote instruments reaching where carbon-based biology cannot safely go. Between these views, a compromise emerges. We send humans where they can survive with reasonable cost. We send machines where human biology would pay too high a price, and Mars, with its unforgiving gravity, may straddle that dividing line. When we weigh these options, numbers begin to matter. Space agencies and private companies do not just deal in dreams. They also deal in budgets. Robotic missions are not cheap, but compared to human expeditions, they are astonishingly efficient. A single flagship rover mission might cost a few $1 billion and operate for over a decade. It needs no life support, no return vehicle, no ongoing medical evaluation. It cannot be homesick. It does not require political will to sustain a multi-year, multi-generational commitment to healthcare for people whose bodies have been altered by another world. A permanent human colony on Mars, however, would carry hidden costs. Continuous medical research, advanced prosthetics and treatments for bone and muscle loss, psychological support from multi-year isolation, potential genetic and reproductive complications from Mars-born children. It would demand a logistics chain so robust that a failure in one supply window might mean famine or mass evacuation. In purely economic terms, robots win easily. In emotional terms, humans are hard to let go of. But maybe the problem is not Mars. Maybe the problem is trying to make Mars into something it was never built to be. If gravity is the fatal flaw, perhaps we look for places where gravity is not a fixed sentence, but a variable we can design. High above Earth, at the Lagrange points where gravitational forces balance like a delicate scale, we could build something Mars can never offer. True, Earth-independent colonies with choose-our-own gravity. Vast rotating habitats. O'Neill cylinders, Stanford Torrey, rings of steel and glass turning slowly in darkness. Inside, forests curve overhead, rivers loop in arcs. Cities stretch along the inner walls. By controlling the spin, we set the gravity. 1G for children to grow bones strong enough to visit any world. Or varied zones, where people can move between light and heavy environments as needed. These stations would not depend on a planet's mercy. They would not be bound to a single world's day, its seasons, its tectonic moods. They would harvest sunlight, mine asteroids, build themselves from the raw materials of the solar system. They would be, in the truest sense, off-world civilizations. In that future, Mars becomes one stop on a much larger map, a place we study, a chapter we read carefully, a world we respect enough not to force ourselves upon in ways our bodies cannot endure. Rethinking Mars is not admitting defeat. It is recognizing that the universe is not obliged to match our fantasies. If Mars cannot be our second Earth, it can still be our mirror, showing us the limits of flesh, the reach of machines, and the kind of future we are truly willing to build among the stars. We began this journey with a simple question: what would it take to live on Mars? Not to visit, not to plant a flag and leave, but to stay, to build cities under red skies, to raise children in a world with twin moons and a distant shrunken sun. And somewhere along the way, we discovered a quiet, immovable truth. Mars is not just smaller, it is less gravity, less protection, less pull to hold a human body together over a lifetime. Its surface looks inviting compared to Venus's hellscape or Jupiter's storms. But beneath that rusty horizon is a fundamental design flaw we cannot patch, cannot terraform, cannot engineer away. Gravity is not a setting we can adjust. It is the stage on which every cell in your body learned how to exist. We can shield against radiation. We can warm the air, melt the ice, even thicken the atmosphere. But we cannot make Mars heavier. We cannot ask a 38G world to do a 1G job. And that leaves us with a choice that is both inspiring and deeply tragic. If Mars truly becomes our second home, it will not be a home for us as we are now. It will belong to people whose bones, hearts, and muscles are shaped by weaker gravity. People who may never safely walk under Earth's blue sky again. A child born on Mars might grow up knowing that visiting the planet of their ancestors would crush them, not emotionally, but physically. To become Martian may mean accepting permanent bodily transformation. Not a quick trip and a return flight, but a one-way evolutionary fork in the road. Or we step back. We decide Mars is a laboratory, an outpost, a place for robots and brief human expeditions, not a cradle for permanent civilization. We keep the dream, but we scale it down, and we keep human defined by the pull of Earth. Perhaps that is the real lesson of Mars. Some dreams do not fit inside our current definition of what it means to be human. To chase them, we may have to rewrite that definition, through medicine, technology, or even genetic engineering, knowing that the result may be something that remembers humanity, but is no longer entirely bound by it, yet uncertainty still cuts both ways. We do not fully understand long-term adaptation to partial gravity. We do not know what breakthroughs in biology, materials, or artificial habitats might emerge. Where there is doubt, there is room for possibility, and for debate. So let's keep that conversation alive. If you found this exploration thought-provoking, tap like so more people can find it. Tell us in the comments where you're watching from. Earth is already a world of many environments. How do you feel about adding Mars to that list? And if you'd like to help us keep making deep dive videos like this, you can optionally join our YouTube membership. It's never required, but but it directly supports the channel and future episodes. Mars forces us to look up, but also to look inward. In the end, the question may not be, can humans live on Mars? But what are we willing to become in order to call another world home?